For the last few weeks, we have been discussing the Bernoulli equation and its derivation and its applications. The last week we discussed about different applications of the Bernoulli equation, like the free jet flow, then the confined flow and continuity equation in relevance to Bernoulli equation. And we also discussed different examples considering the free jet flow and the confined flow. And then we also discussed that another application of the Bernoulli equation is the flow rate measurement using different type of flow measuring devices like the orifice meter, nozzle meter, and the Venturi meter. And we discussed in detail how the flow rate is measured using the Bernoulli equation and the continuity equation. We also discussed flow rate measurement in open channels using the slice gate, and we reached this result that for slice gate the flow rate is measured using this equation, which is basically dependent on the height or the elevation of the opening of the gate into the free fall velocity of the canal due to difference in elevation. So today we are going to discuss another important topic related to the Bernoulli equation, that is energy line and the hydraulic rate line. Energy line is basically, first of all, we need to understand the head form of the Bernoulli equation. We know that the Bernoulli equation is P plus half rho V square plus gamma Z equal to constant. This is the pressure form of the Bernoulli equation, and we know that P is called the static pressure, half rho V square is called the dynamic pressure, and gamma Z is called the hydrostatic pressure, and C is called the total pressure that is constant along the streamline. If I divide this whole equation by gamma, which is the specific weight of the fluid, that is, I divide this by P this by gamma, I divide this half rho V square by gamma, I will get V square by 2G, right? Because gamma is density into gravity, gamma is rho G. So we have rho in the denominator in the second term, so we will only be left with G. So V square by 2G plus, here we will have only Z, which is the elevation, equal to capital H. In this equation, P by gamma is called the static head. V square by 2G is called the velocity head, and Z is called the elevation head. And H is called the total head, which is constant along the streamline. So the sum of these three heads, that is static head, velocity head, and elevation head, is called the total head, and it is constant along the streamline. Each of these terms is representing a certain height, a certain quantity in meters or feet. Is it clear?
Yes, sir.
So if we are familiar with the head form of the Bernoulli equation, then we can draw two lines, that is the energy line and the hydraulic rate line. Energy line is basically the total head. Energy line represents the total head. So if I draw any line that is representing the total head, it will always be if I draw any line that is representing the total head, that is a fixed value, that line should always be a horizontal line, right? If the line is constant, the value is fixed, that would always be a constant line, right? So for any flow, energy grade line will always be horizontal, right? So this is the energy grade line, and it will always remain horizontal, fixed, because it is representing from certain reference. Let's say this is the flow path, and from certain reference it is representing the total head. This is the H, total head, which is sum of these three heads: static head, velocity head, and the elevation head. On the other hand, the hydraulic grade line or HGL. For any flow, it represents the sum of static and elevation head. So if the static and elevation head are not changing, then the hydraulic grade line will be equal to the energy grade line. But if there is variation in the static head or the elevation head, then the hydraulic grade line will be different from the energy grade line. How they are drawn, we discuss it through an example. Let's say we have a flow like this, as shown in the figure here. So I bring it here. For this flow, we're interested in discussing the hydraulic grade line and the energy grade line. Okay. Well, this is the datum point, this is datum line, this horizontal line at the bottom. From this, we'll be measuring all the references. This center line here from this point to this point is your flow line or the streamline along which we are applying the Bernoulli equation. So in order to, we will use this reference to indicate the जी हारिस क्या बात है? Is everything all right?
सॉरी सर वो माइक का पता नहीं था क्या हो रहा है.
ठीक है जी. So this line along the center is representing your center line. This bottom line at the bottom horizontal line is representing your datum or the reference line from which we will be measuring all the values. So distance from this bottom line to this center line is the elevation of that point. This is the elevation. So in this pipe, if I install a static tube at this point 1, let's say, if I install a static tube at point 1, what it will indicate, what value it will be measuring? The reading on the static tube will be showing
static head.
The static head. Okay, so we know the elevation head because we can measure it from the reference to the center line, and from the radium static tube we know that this is the static head. So this is the point for the static head. If I install a pitted static tube at this point, what it will measure?
Stagnation pressure.
Which is the sum of the
dynamic pressure and hydrostatic pressure.
Dynamic and the static pressure, not the hydrostatic pressure. The static head and the dynamic head. So the difference in the readings of the two will give us this difference. This height will give us the dynamic head, right? The difference in the reading between the static tube and the pitted tube will give us the static head. So this is V1 square by 2G. As we move further along the pipe, and if we install different static and pitted tubes at different locations, we come to know that as the area is decreasing, the velocity will increase. So we know that energy line will represent the total head, this edge. So it will always remain horizontal. So once we draw the energy line, this will remain fixed along the flow. This will always remain fixed along the flow. But as we move along the pipe, along the center line, we see that the area is decreasing, so the velocity will increase. Increase in velocity means that the static head will decrease. So the hydraulic grade line, which is the sum of the elevation head and the static head, will fall below the energy grade line. From this point, energy grade line will start, hydraulic grade line will start dropping. till the point the velocity is increasing. If certainly there is change in area and the area increases, so the velocity will decrease and the hydraulic rate line will move upwards. Clear?
Yes.
So this is how we draw hydraulic grade line or the energy grade line, or in reverse, if we are given the hydraulic grade line and the energy grade line, we can extract information from, we can extract information about the velocity head, elevation head and the static head. Okay, is it clear?
Yes, sir.
Okay, we consider another example where we discuss the hydraulic grade line and the energy grade line. So consider this flow situation. In this flow, initially you have a static fluid in a tank, and this tank is connected to a flow line that has a change in area. Starting from point 1, we are interested in drawing the hydraulic grade line and the energy grade line along this flow. So at point 1, there is no flow, so this hydrostatic pressure, the only head is the hydrostatic head, that is Z1. So this is the hydraulic grade line as well as the, and we know that the energy grade line will always remain horizontal because it's representing a total head, and we know the total head is H. So we draw a horizontal line representing the energy grade line, EGL, right? Energy line or the energy grade line. This red line. So from point 1 to this point, we'll have a horizontal energy grade line. What about the hydraulic grade line? We reach this point and we see that certainly there will be a flow, and that flow is coming at the expense of the change in the area, because the area is suddenly decreased, so there will be a velocity increase, and that velocity increase is coming at the expense of the static pressure. So the static pressure will drop and we'll have this V2. If we can calculate velocity 2, we can draw the hydraulic grade line. The difference between the energy line and the hydraulic grade line is the velocity head. Then the hydraulic grade line will remain constant till the point the area is not changing, the area is fixed. When we reach this neck, there is another change in area, and that change is decrease in the area, which means there will be more change in the velocity will increase more. So the static pressure will further drop, so the energy grade line will start, hydraulic grade line will start dropping till we reach this exact point where the static pressure is 0 and only we will have the elevation head and the velocity head equal to the total head. So the hydraulic grade line will again remain horizontal. Is it clear?
Yes, sir.
Yes.
Any question in hydraulic grade line or the energy grade line? If it is
सर ये
clear,
जब एरिया डिक्रीज होगा तो स्टैटिक प्रेशर डिक्रीज हो जाएगा ना?
yes, decrease in area will mean increase in velocity, which means increase in dynamic pressure, or the velocity head, which means decrease in the static pressure. That increase in velocity is basically coming from the decrease in the static pressure. Static pressure is being converted into
सही है
the
सर.
velocity. So if it is clear, we are going to solve different problems related to the Bernoulli equation. So in order we can have a better idea of the Bernoulli equation and its applications. So starting with this problem number 1, we have, I will just be guiding you. You will help me in solving the problems. Okay. So in this problem 1, we have water in a tank, and there is a light liquid on top of the water. So there is a layer of a liquid on top of the water, and then there is water that is having elevation of 4 feet, and then it is connected to a tube from which the water is flowing at a speed of 10 feet per second. You are required to measure this depth H of the light liquid that is responsible for producing this much velocity of the water, 10 feet per second. Is it clear?
Yes, sir.
So how will you solve? How can you calculate the height h?
टोटल हेड की इक्वेशन लिख देंगे इसमें.
Okay, total head equation at which point?
सर 4 फुट पे और 5 फुट पे.
So we will choose 2 points. We will write, let's say, this interface as point 1 and this exit as point 2. Since point 1 and point 2 are both in water in the same fluid, so the total head from point 1 should be equal to the total head at point 2. So P1 by gamma of water, because water is the fluid, plus V1 square by 2G plus Z1 should be equal to the total head at point 2, that is P2 by gamma of water again V2 square by 2G Z2. Okay, is that clear?
Yes.
Now we can apply some simplification on this equation. First, we need to establish from which we will be measuring Z1 and Z2. Let's say we define this bottom of the tank as our reference from which we will be measuring Z1 and Z2. Okay?
Yes, sir.
So Z1 would be 4 feet and Z2 would be 5 feet, right?
5.
So we know Z1 and Z2. What about P1?
Sir, gamma H.
P1 would be gamma of the light liquid. If we call it, let's say it's some oil. So P gamma of oil into the elevation H, which is unknown to us. Clear?
Yes.
What about V1?
0, sir.
So V1 is 0 because it's a large tank, free jet situation. What about P2?
0, sir.
0.
Because it is discharging into the atmosphere, so P2 is also 0. V2 is given to us as 10 feet per second. So we can write the equation now in terms of all the known. So P1 is gamma of oil into H divided by gamma of water plus 4 equal to 10 square, which is 100, divided by 2G, which is 20, if we take the value of the gravity as 10, plus 5. We know gamma of the oil, we know gamma of the water, the only unknown is H. So we can rearrange the equation to calculate H. We'll just write the value of H here. So we can write 100 divided by 20 plus 5 minus 4, answer multiplied by gamma of water, which is 62.4, divided by gamma of oil, which is 50. So it is 7.48 or 7.5 feet. Clear? This is 7.5 feet. Any question in this problem solution? Anything which is not clear?
P2 0 क्यों किया है सर? हाइट तो है उसकी.
P2 is static pressure, which is equivalent to the atmospheric pressure at point 2, because point 2 is located at the discharge of the pipe, and that discharge is into the atmosphere. So P2 is basically atmospheric pressure, and we are taking gauge value of the atmospheric pressure, which is 0. Clear? We have discussed this in detail in the free jet application. Yes.
सर आंसर मेरे पास 3.17 फीट आ रहा है सर.
कैसे भाई?
सर आई गेस
सर आपने G की जगह पे सर वो 9.81 की वैल्यू ले ली है शायद सर 32.4
yes,
लेंगे
yes.
सर
Thank you.
32.2 आएगी.
Here we'll have not 2 into 32 point. Thank you very much for the correction. 32.2. I have taken value in SI units. Sorry. So we'll just 32.2. So we'll have. Yes, it is. What's your answer is 5.12.
सर 3.17
3.17.
No, it should be 5.11. 100 divided by 2 into 32.2 plus 5 minus 4, and then we'll have 2.55 into 62, 3.18 feet, right? So it is. So that is 2 into 32.2. So any further queries in this? Is it clear?
No, sir, clear.
Okay, then we solve another problem related to the Bernoulli equation. We're going to solve different problems so we can develop a good comprehension of the Bernoulli equation and its application and how to apply it in different flow situation. So in the next problem, we have water that is flowing through the pipe contraction as shown in the figure, and there are two tubes installed at this pipe. One is a static tube installed at the pipe having larger diameter, and then there is another fitted tube in the small area or the small diameter tube, and the difference in the reading of the two tubes is 0.2 meters. You are required to determine this flow rate Q. So how can we solve this? Any ideas? First, we will need to define a center line, right, or the reference line. This is the line along which we will be considering the flow, and then we will define 2 points. Point 1 at this location and point 2 at this location. And if we write the Bernoulli equation between 2 points, what it will be? Anyone, Ji?
सर प्रेशर P1
At point 1, P1 by gamma, right?
yes sir
Velocity,
sir
P1
velocity
square by 2g, right?
yes sir
There is no need to write the elevation head because
yes
it's a
sir that
horizontal
will be
flow.
same
At point
Same over.
we'll have P2 as, we'll write P2, right? Because we don't know what is V2. What is V2?
so V2 will become 0
Because it's a stagnation point, so there will be no velocity. The flow will stop at this point, so
yes
V2
sir
is 0, and there is no elevation head as well. So if we see this equation, we have basically three unknown, right? P1, P2, and V1. So what's the other information that can help us to eliminate
sir
the
we
other
can
unknown?
apply
Manometer
the
you
flow
can
rate
set
equation
sir.
on both the points
YouTube
to find out V1
No, we can use these readings.
Height
Let's say
differences with the
Sir,
pressure difference.
YouTube manometer.
if I say that the reading on this static tube is X, let's say the reading from center line to this static tube is X, what it would be representing? This X would be equal to the static pressure, right, at point 1.
yes sir
So P1 by gamma should be equal to
X
X. then the reading here is what? It is equal to x plus 0.2, right? In the pitted tube, right?
Yes, sir.
Yes,
And
sir.
this would be equivalent to P2 by gamma,
Sir, this will be P2 by gamma.
right? So it is x plus 0.2. So basically V1 square by 2g equals to 0.2, right? If I see these two equations and this equation, I can easily say that this difference of reading is basically representing the dynamic head, right? Or the velocity head.
Yes, sir.
So V1 square by 2g equals to 0.2 meters, right? So we can simply rearrange this equation to get V1. So what is V1? 0.2 multiplied by 2 multiplied by 9.81 square root.
One 1.98, sir.
1.98 meter per second. So if we know V1, can we calculate the flow rate? Basically, we are interested
Yes,
in
yes.
calculating flow rate Q.
A1, P1.
So the flow rate can be calculated using equation Q equals to Q1 equals to A1 into V1. And area 1 can be calculated because we are given the diameter of the pipe at 0.1, which is 0.1 meter. So pi d square by d1 square by 4 into V1. When we solve, what we get the
0.0155.
0.0156 or 0.016 meter cube per second. Is it clear?
Yes, sir.
Any question in this
Yes.
problem? Is it clear to everyone?
Clear.
Okay. Moving further, we solve another problem. The purpose behind solving this much amount of problem is that you can become familiar with how to define the points for applying Bernoulli equation and how to simplify different terms in the Bernoulli equation and how to define the datum. Otherwise, it's a very simple trick to apply Bernoulli equation. Just define 2 points, write all the terms and solve for the unknown. So in this problem, you have a smooth plastic garden hose. This is basically a garden hose, a pipe, which is also a small diameter pipes are called usually hose, with an inside diameter of 20 millimeters. And you have placed it in a swimming pool. And due to this slope, this tube is draining the pool. You are required to calculate the rate at which this pool is being drained, at the rate at which the flow is happening from this hose. Can you solve this problem?
Yes, sir.
First, we will need to define two reference points on which we will write Bernoulli equation. So those reference points can be defined at which locations? Any ideas?
Bottom of the container, swimming pool.
No. If I define it at the
Bottom
bottom, that
Sir,
will
top
become
of the pool and
Top
the
of
opening
the
of the pipe.
point
The
1
top of
will
the pool
define
and
at the
opening.
surface and second at the exit of this hose, right? And then we need to define the
तो इसमें सर ये
reference.
बता दें कि किस तरह डिफाइन करते हैं ये पॉइंट्स कहाँ पे डिफाइन करने हैं.
This is basically based on the theory we have already studied. If I consider this situation, this is a free jet situation, right? We have a container that is filled with liquid and we have a pipe from which the liquid is flowing. So we know that for free jet, on the free surface, the velocity of the fluid will be zero. The pressure of the fluid will be zero. So it will more simply that the only the head that would be involved at the free surface would be the elevation head. So we see that the best point is point 1. We can define point anywhere. Like I can define it in the middle of the pool, but then I will need to consider P1. I will need to consider Z1, right?
सही हो गया सर, समझ गया.
So second point we can define anywhere in line at this point, but the most simpler point would be exit. Why? Because the exit would be in the atmosphere, discharge will be in the atmosphere, so P2 will be 0, right? And we can calculate velocity V2, which will be unknown to us by using the equation between point 1 and point 2. Now we define the datum or the reference along this horizontal line. Okay, this is the line from which we will measure the elevations. This is our reference line. So if I ask you to write Bernoulli equation at point 1 and equate it to the Bernoulli equation at point 2, how will we start? P1 would be
0.
0. Velocity at point 1 would be
0.
0.
So the total head is
Zero.
only the hydrostatic head, that is Z1. This should be equal to the Bernoulli equation or total head at the point 2. So at point 2 P2 is
0, sir.
0, sir.
0, so we don't need to write that. V2 is unknown. There will be velocity V2
Unknown,
square
sir.
by 2g, and there is, because the pipe or the hose is located below the reference, so there is some hydrostatic head as well. So we'll write Z2. Clear?
Yes, sir.
Z1 is equivalent to, from reference it is
0.2, sir.
0.2
0.2.
meters.
0.2.
0.2, and it is equal to V2 square by 2g. Z2 is
Minus 0.23.
Minus 0.
yes, it's below the reference. So the upward direction is taken as positive and the downward direction is taken as negative. So it is minus 0.23 meters. So we know all the values here except V2. So we'll just calculate V2, 0.2 plus 0.23 multiply by 2 multiply by 9.81, and then we take the square root of the answer. It is 2.90 meter per second, right?
Yes, sir.
2.9 meter per second. So we can calculate the flow rate or the rate at which the pool will be drained by using Q equals to area of the hose, which is, because we are given the diameter, we can calculate the area, and velocity we have already calculated using the Bernoulli equation. Clear?
Yes, sir.
Yes, sir. सर ये थोड़ा सा ऊपर करके डायमीटर दिखा दीजिए.
20 millimeters. Diameter is
Okay.
20 millimeters. Okay. So we can calculate area too. We know the velocity, so we can just calculate the flow rate. Then we have another problem to solve. That's another just description to help us to solve the Bernoulli equation. That's a bit interesting or a bit challenging one. So I would be delighted if you can help me to solve this problem. It will mean that you have understood the Bernoulli equation very well if you can solve this problem. So there is a water tank and there is a pipe, U-tube shaped pipe that is put into the tank, and then there is a flow generated in this pipe. You are required to determine the flow rate from the tank, like flow rate at any point at the rate at which the flow will be happening, and the pressures at point 1, 2, and 3 if the viscous effects are negligible. Point 1, 2, and 3 are already defined, and you need to measure the pressure P1, P2, and P3 at these 3 points. Okay, how you will proceed with this problem? In order to calculate the flow rate, just a hint to you, you need to know the velocity at any of these points, at point 2, at point 1, or point 3.
Sir, velocity same होगी.
Yes, they
No,
will be
sir.
same, but how you will calculate the velocity? That's
Sir, वो change in elevation. रेफरेंस पॉइंट सरफेस ऑफ द कंटेनर लेंगे और सेकंड पॉइंट जिस पॉइंट वेलोसिटी पॉइंट
we see that there are two
मतलब
additional points in this problem, right? That can help us to simplify the problem. One point is this surface point. We label it as 0.0, and the other point is this exit point, and we label it as 0.4. If we apply, these are the 2 points that will simplify the equation very much. That will reduce the number of unknowns in the equation, right? And we
Yes.
use the bottom of the tank as our datum point, measure the elevation as the reference line. So now if I ask you to write the Bernoulli equation between point 0 and 4, what it will be? Starting from point 0, P0 would be,
So 0.
V0 would be,
0.
we will
0, sir.
only have Z1, which is
5, sir.
5.
5 feet. So we'll write just 5 equal to the equation at point 4. I am writing equation between 0 and 4 points. So you are not confused. At point 4,
Sir, P will be 0.
Sure.
And
P will be 0 because it is discharging into the atmosphere, right?
Atmosphere.
V4,
sir, V4 by 2G.
V4 square by 2G, right?
And sir, Z will be 0 again.
And Z will be 0 because it is at the reference line, okay? So we don't need to write that. So we can just calculate V4 equal to under root of 10 times of gravity. Clear? So under root 10 into 32.2, which is 17.95 or 17.94 feet per second. Clear?
Yes, sir.
Now flow rate is not a problem because velocity at all the points, flow rate at point 2, 1 or 3 will be fixed. So we can calculate just Q by using A4 into V4. We also know that there is no change in the area. The area of the pipe is fixed, the diameter of the pipe is fixed, so we can write V4 equals to V1 equals to V2 equals to V3. Now the pressure P1, the pressure P2 and the pressure P3. So what will be P1? Again, we can see that point 3 and 2 are at the same elevation, right?
Yes, sir.
Yes, sir.
So it means that P2 and P3 would be
Same.
same
Same.
because the area is not changing. So and the elevation is not changing. So the static head will remain fixed as well. So we need to calculate P2 in order just so we can apply equation between point 2 and point 0, point 2 and point 4, any of these 2 points, okay? So in order you just apply Bernoulli equation between point 2 and 4. To calculate P1, you can apply Bernoulli equation between point 1 and 4. That you can simply do. That's not a challenging task. My question is to you is that will P1 be greater than P2 or it will be less than P2?
Sir, P1 lesser than
Less
P2.
than.
Why?
Sir, because the height is greater, so it should be smaller for the
At point 1, the total head should be constant. It should be equal to the head at point 0, head at point 2, head at point 3 or head at point 4, the total head. We can see that the elevation head at point 1 is greater than the elevation head at point 2 and 3, which means there will be a decrease in the static head at point 1. So P1 will be less than P2 or P3 or P4. Clear?
Yes, sir.
4 पे तो 0 हो जाएगा ना, P4 पे तो all the pressure will be converted to the velocity. There is no elevation head, there is no static head. All the head is the dynamic head. Clear? Any question in this problem? Clear?
Yes, sir.
Yes.
Okay, this last problem is your home assignment. This is again a very simple problem. You have a flow that is not horizontal this time, but that is inclined. So we will define a horizontal reference line. And from that reference line, you will measure the point. These two black dots will be labeled as point 1 and point 2. You will measure the elevation heads. And using these readings, you will be calculating the height h, because you are interested in calculating this height h in the YouTube manometer. Clear?
Yes. Yes, sir.
This is your home assignment. This is a homework problem. You will solve it and you will let me know if there is any problem in that. Clear?
Okay, sir. Okay, sir.
Okay, sir.
With this, your chapter number 3 ends.